All right, our last focus on converting alcohols into better leaving groups. You ready? That's what the morning's been about. We're going to make two different secondary RXs. Secondary RX, secondary. What's X again? Clearly not in this first example. A leaving group. And what was your definition of leaving group? The conjugate base of what kind of acid? Yes, OSOO with a phenyl and a paramethyl is called OTS negative. Conj base of, it's the conjugate base of, it's similar to sulfuric, but I wouldn't say it's identical, but it's the conjugate base of toluene sulfonic acid, which is hot, which makes it a good leaving group. Yeah, alcohol, not a good leaving group. And talk to me about the stereocenters. R still R when we're finished with this one, but R becomes S when we do this one. Wow, that gives us great flexibility, because we can start with either one stereocenter and end up with either one on a carbon that has a leaving group. This is very good stuff. The mechanism will show us why. There's a good reason why I put these two together. The first two steps are identical. So put a lone pair on your alcohol. What is the most positive atom on the page here? And it's because it's got, in the top example, 5 bonds to more electronegative things. And in the bottom example, it has 4 bonds to more electronegative things. What atom is the most positive on this page? Sulfur. Now, when you attack an atom and have a choice of breaking a sigma or a pi, the answer to that question, which one, is always the same. Which one's weaker? You're telling me sigma bonds are no weaker than pi? When did they change that? I missed the memo. No. Pi has p orbitals overlapping, which are never between the atoms. They're above and below. That's a pi bond. A sigma bond has electrons directly between the atoms. In which scenario are you a happier pair of electrons? When I'm right between two nuclei, that's as close as I'm ever getting to protons. Sigma bonds are stronger than pi. You got to break pi first. There you go. Same story here. Break sigma. So you guys got me going. Break pi first. Don't get the teacher going. So that there, hey, that's good. They're the same. The results are similar so far. We got our carbon. Carbon green today in this one. I got my original OH still there. I got my original H here. And sadly, I don't think I left enough room for my new group, but I'll do it anyway. Put it in black. It's got a sulfur that now has an O- on top, and a Cl, and a double O. And what do you do in organic chemistry when you don't have enough room, but you want to draw a group that's already been drawn once? I can circle it and call it R. We'll circle in purple, because I don't want to draw this thing ever again on this page. And that means sulfur also has an R group. I'll sneak it off to the left here. Look at that. This one down here, very similar story. Oh, I'm going to lose a half point because I didn't put a charge on my oxygen. I got it back. I got my half point back. Got an O with an H. It's an oxonium. Got this sulfur here that has an O- on top, like the one up there, Cl here and a Cl here. So the first steps are over and they're identical, aren't they? The second steps are identical. O minus comes back, makes a pi, and a leaving group leaves. O minus comes back, makes a pi, and a leaving group leaves. What do you call reactions that make a pi while a leaving group leaves? We did it Monday. It's written vertically on your notes. You haven't looked at them yet, I know. It says these blank reactions create blank bonds. Elimination, good. I was giving you terrible clues and you still came up with it. Thank God. Thank you. Yeah, I know there's pretty dynamic weirdness there with the vertical elimination. So we're doing elimination reactions here. That's what happened. Can I write elimination, jog your memory here? Try to use your new words as many times as you can. Helps you learn them. And you get a new pi. I think I need to extend those blue arrows, okay? I just don't have room to draw stuff here. Just go to the other side of those big boxes. Yeah. And you've got this. And this. This one's almost done. And you got your S double O twice with your hey, I got the R, right? Purple R. And a plus charge here. We'll talk about how to go there. Down here, you got similar situation. And you got your S. And it's back to a double bond to O, but I only got one this time. Cl. And you made a Cl minus this time. And I think you made a Cl minus this time too. Yeah. I'm trying to show something here. There's the Cl minus. You see it? You made it during the elimination. Next step's the same. So I said first two steps are the same. First three steps are the same. What's this thing under the arrow? You ever seen it? Under the arrow, both reactions. Describe it. What would you say this looks closest to, based on things you know already? This thing. It looks like a phenyl. In truth, phenyl, when it's a molecule, is called benzene. It looks a lot like benzene, right? The fact that that nitrogen was a carbon, it is benzene. So this one's called pyridine. Pyridine. And it's what we call a proton scavenger. Pyridine. And I got to translate proton scavenger for you. Azabenzene. She asked for the IUPAC name of pyridine. You would say aza, A-Z-A, benzene would be its IUPAC name. But all organic chemists call this thing pyridine. We have to learn that because it's very common. We use it a lot in lab, and we got to know how to name it. So pyridine is a proton scavenger, which is, I translate for you, it's looking for strong acid. That's all it knows how to react with. It won't react with a weak acid, not quite a good enough base for that. But I think at this juncture, we have a strong acid. Give me a pKa for these two acids because they're almost identical. Based on what you know already. It's an oxonium. Say it again. -3, good answer. It's a strong acid, that means pyridine can do the job. Now, at the beginning, was pyridine a strong enough base to grab the H off of an alcohol? What's the pKa of an alcohol? 17. Yeah, 17 does not go towards 10, which would be the ammonium ion. That's what you know about ammonium ions. It's about 10, right? This one's a special ammonium. It's not quite the same as 10, but the idea is the same. No, you can't scavenge anything but a strong acid. What I'm trying to say is don't take the H off early. A lot of you said, hey, these mechanisms are easy. In fact, I'm going to show Dr. Whitaker. I found a faster way to do most of his mechanisms. And you were the people that got the in this universe speech. About 5 of you. In this universe, that base doesn't take the H off of a molecule like that. pKa says no. Okay, so yeah, take the H off when you have an acid that's strong, and that is not until now. And pyridine is the is the species that's going to do that. You need a lone pair on your pyridine. There's going to be one wandering arrow here, okay? Want it pink so you can keep track of it? There's a pink arrow coming up here. Look at that. Is that our longest arrow of the semester? Same story here. So you definitely want to study these mechanisms together, right? Up until now, they're exactly the same. That top one is done. You are in the box. Bottom one is not done. You have to draw your new result. Forgot my H. Wouldn't have deducted any points. That does not look like what's in the box at all, does it? Okay. All right. So here I have a secondary RX, right? And this one be a secondary X. Let's look back a second. Yeah. Here Br minus is doing a backside attack on a carbon with a leaving group. I'm going to make a comment, retrofit a comment. You don't have to retrofit a comment. PCl3 does not work because Cl minus is not a strong nu like Br minus. Wow, that you didn't know. You thought they'd all be the same. You really did. That's a natural instinct. They're grouped as halogens, right? They should behave the same. But Cl minus with its high electronegativity brings that minus a little closer to the nucleus. It's not quite as reactive as Br minus that has that minus way out here. It's just a bigger atom. Okay? So this step will not happen if this is Cl minus. And the reason I'm bringing it up, Cl minus is not a good enough nucleophile to attack this secondary carbon with a leaving group. It's not. There is Cl minus here. You made it right here. It does not hit this thing. So how then can this Cl minus attack this thing? What's different? Why does this happen here but not in the reaction above? You want the strangest answer? I don't expect you to understand this answer. I'm going to give you a one-letter answer. You ready? Watch. Here's the one-letter answer why this reaction happens down here and not above. Whoa. What is he saying? How can that be an answer? He's put a state. That's a state. What state is that? Gas. So the reason Cl minus does not attack this, one, Cl minus is not a good strong nucleophile. We knew this from the previous comment, right? Why does it attack this one? Well, this is more reactive than this because of entropy. This is not a good leaving group. It's not even an excellent leaving group. It's better. It's superlative. It's the bee's knees. It's the bestest ever. Supercalifragilisticexpialidocious. Some of you still know what that means. I'm impressed. That's like Disney from 1950s, guys. Anyway, if you can have a gas, that's the best possible leaving group. That's all I'm trying to say. It's exceptional. How's that? That's a good word, right? Exceptional. Better than good. So the only reason you can induce Cl minus to be a nucleophile here is because this thing is leaving as a gas. Okay? This thing will not be a gas. That's your traditional leaving group. It's not going to do anything until you have a reaction where you have a strong nucleophile. Yeah, for you though, because you know we're seeing very limited gases leaving in this course. SO2 in this course is your only gas you're ever going to see as a leaving group. And wait till Orgo 2 where you see nitrogen gas quite frequently and see how to do that. But you're not going to have that this semester. So just focus. The SO2 gas, great leaving group. Better than good, better than excellent. And this will reliably get you to these species here, right? That one and that one. And why did the stereo center flip? What do you call this kind of attack and this leaves? Backside attack does what to an R stereo center? Inverts it to an S stereo center right here. That's good. I like when themes recur. Makes them easier to learn. All right.